So maybe it is a problem or some small problem. I hope it's not the screen. Because I think it looks like a display card. If the display card is gone, I cannot fix it.
Okay, good morning everybody. Thank you for being here for the second day of the MEDES conference. It's our pleasure today to introduce a very distinguished personality in research and education, Professor Michael Papazogloum. We know very well him as Mike in general. So Mike is chair of computer science at Tilburg University in Netherlands. He's also executive director of the European Research Institute in Services Science, and also scientific director of the European Network of Excellence in Software System and Services, SQ. Mike is a very recognized international personality, leading a lot of projects and innovation in different areas like computer science, information systems, industrial engineering, and digital manufacturing. As when we are working in this area, we know that we can consider Mike as the father of service-oriented computing. Okay? He has a very prestigious and successful experience leading research excellence in Europe, China, Australia, and United Arab Emirates. He has also a very large experience leading top-level innovation research actions in distributed systems, cloud computing, service-oriented computing, and recently in smart manufacturing. Mike is also author of the most highly cited papers in the area of service engineering and web services. He has an amazing record of 23 books in the area and more than 200 prestigious peer-referred papers in this area. He's also a distinguished honorary professor at 11 universities around the world, and he has been excellent delivering the keynotes, and we are really pleased to have you today to talk us about Internet of Everything. Thank you very much.
Thank you, Ernesto. Thank you. You make me blush. And it's very early in the morning. I'm not coffee. Thank you very much. I really appreciate the invitation. It's a wonderful place and a very interesting conference, and I'd like to thank the organizer, of course, my friend Ernesto, and also Roger for inviting me here. Richard for inviting me here so early in the morning. So too much wine last night. Hopefully I have the right talk for you here. Okay, so basically what I wanted to talk to you about is an emerging field. So this is an amalgamation of a lot of trends, and I couldn't describe it. So I was looking at the internet to find a nice term for it, and I bumped accidentally into a term which was introduced in fact by Intel and Cisco, which is called the Internet of Everything. And I thought this is really fantastic, because this is what I mean. And what I did is I have put some thoughts and some ideas together, and especially research areas which are open research areas and several problems which come from diverse fields. Now, what I decided to do at the end of the day, I wanted to use a particular vertical, if you wish, sector to use some examples. And I decided to use manufacturing. So don't let me scare you with the word manufacturing. It's much more easier than you think. So I'll try to have a sort of short introduction to the topic, and then I'll introduce you a little bit to manufacturing to see what ideas may be used from computer science, of course, and IT, and be applied to other areas, other sectors like medicine, manufacturing, and so on. So without further ado, let me go through the agenda. It's a long agenda. I know that we have roughly an hour, so I'll try to squeeze it. Basically, I will start with a vision. Then I'm going to talk to you about research challenges and trends. And then I'm going to go to the topic of smart connected factories. We'll talk a little bit about big data and analytics in smart connected factories. There's an emerging trend, a huge trend, which is called Industry 4.0. Maybe a lot of you have heard about it. It's coming from Germany in particular and the European Union. And what I'll try to do is I'll try to address some of the challenges that I mentioned here in the context of Industry 4.0. And I will give you some examples of our work in that particular sector. And I will close with a few remarks, general remarks. So let me get started with the vision. Now, if you ask me for a definition, and I suppose this is the first thing that you're going to do, ask me what the Internet of Everything is, then I'm going to tell you that there are 4 elements which are somehow inherently, if you wish, integrated, the part of this search, if you wish. There is, of course, data. So data is the fuel of everything. Now, everybody speaks about big data today, which is perfectly fine. But what we are doing is we look at big data in isolation. And this is one of the biggest problems that we have. We're making the same mistakes we made 20, 30 years ago. We start getting excited by a particular topic. We invest all our energy in one topic, and then we neglect the rest of what we've been doing for the past 10, 20 years. So what I want to do is I would like to have a holistic approach. So there's 3 elements in this slide which I want to interconnect and interrelate, because this is important. The second dimension here is processes or services, which is very close to my heart. And this is an area I've been working for over 15, 20 years now. This is very much connected to the data. So if you think in terms of the data, you need to identify the processes or the services under which the data operates. If you look at those 2 things in isolation, then you're doing something wrong, probably. But who knows? The other thing is, of course, the Internet of Things and things, which is perfectly fine. So these 3 things have been looked also in conjunction by several researchers. The missing element in the puzzle is this one. And this is a very important one. It's been neglected all the time. A lot of people, of course, are working on user interfaces. I'm not denying that. This is an important area. But they don't look at it in conjunction with the rest. So they look at it again in isolation. So what is interesting here is to look as people as part of the process, people as a service, people as part of the entire, if you wish, supply chain or the value chain, because people is an integrated, if you wish, element of that. And this is what I'm going to try to explain to you a little bit today. Now, if we look at the vision and if we look at what is happening, there is a whole heap of applications which we call smart solutions or smart applications. And they come from different, if you wish, sectors. So we have smart traffic, smart cities, businesses, food systems, agri-food, of course, healthcare, water management, supply chains, telecommunications, and so on. And the underlying characteristic is something which we call smartness. Now, what is smartness? Well, at least smartness in my vocabulary is that you have an unobstructed visibility of all your services and all your data. So you have a global view. And you try, of course, to optimize your resources. At the end of the day, what you want to do is you want to provide help and guidance for people to make efficient and effective decisions. So basically, the idea is our systems are more intelligent, more proactive, more smarter, if you wish, at the end of the day. And what they try to do is they work together with humans to improve decision making and solve quite complicated problems. Now, if we go back, there was a search, probably a lot of you remember that, about 15 years or so ago, which was called I guess, semantic web services. I was completely against it from the very first moment, simply because these people were saying we automate everything and everything happens automatically. And I was saying, no, this is not possible. Now, 10 years in the future, we come back to this problem and we say that humans should be an element of the computation, an important element. And at the end of the day, people are the ones who have the decisions, not computers. Computers are there to help us. So we want to plan a coordinated response to a very complicated, or if you wish, individualized application. And this is what I'm going to show you a little bit later on. Now, if you guys have questions, don't hesitate to interrupt me and ask me. Don't save them for the very last sort of minute. So it'd be nice to have a bit of an interaction. I know it's a bit early in the morning, but if you had a nice breakfast and a coffee, maybe we can have a bit of a discussion here. So let me talk to you about the challenges and the trends. So first of all, what we have to observe is that the market is very fragmented. So what we have is we have hardware, we have software, we have protocols, and there's a complete lack of integration. There's a whole heap of interesting tools and interesting developments. You have MapReduce, you have Hadoop, you have whatever you have, but these things are somehow disintegrated. So what we want to do is we want to start looking at how we can put these things together. And what we want to do is we want to develop new generation of applications which are smarter applications, and in fact they're more interesting because they are applications which are in a position to support the users by proposing different paths of computation. So the idea is not that there's a single answer to a problem, but there are many answers and you pick and choose the one which is optimal, the one which is tailored to your needs. Now, unfortunately, a lot of options are closed. You have a lot of interesting approaches, a lot of interesting prototypes, but they are rather monolithic solutions. They work for a small problem. They have maybe some beautiful solutions, but then again, if you want to put them on a broader context, then of course, unfortunately, they don't reciprocate. So basically, what we want to do is we want to look at what challenges there are there and what type of research we can do. So what I did is the past 4 or 5 years, I went through a series of conferences in the areas of services, business process management, CPS, big data, and so on. And I picked and chose several topics which I organized into, if you see here, a few broad areas. So 3 broad areas, very broad areas, in fact. So science and engineering foundations, systems engineering, and applied development and deployment. So these are very broad areas. And here what I did is I lined up a few interesting topics. So if we look at the first area, we talk about robust, effective construction of systems and infrastructure. So this is very much a systems approach, if you wish, developing new infrastructures based on cloud computing, big data, and the like. So basically here what we would like to do is we want to devise cost-effective systems, we want to design them, we want to analyze them in development, create domain-specific architectures and frameworks. So what we have observed in the past is although there are similarities between certain domains, you cannot really have a generic solution. So there's not one solution which fits everything. So if you look at different domains, you're going to find out medicine is completely different. For example, if you compare it to smart cities, there are some overlaps, of course, but again, there are individualities which you need to take into account. Now, you want a more seamless human integration as part of the problem, assumption-based options, analytics, improved decision-making, and so on. So you want a system which is rather proactive, which comes back to you and says, hey, have you looked at that? Are you aware of the fact that your systems are out of sync and you're going to lose on performance, quality, what have you, if you don't do something about it? These are the types of systems that I have in mind. So proactive systems which are able to pick up signals and events and try, if you wish, to inform the user or the developer upfront before the problem happens. If the problem happens, it's far too late. Now, if we look at systems engineering, which is very much related, we want improved performance, quality, assurance, and of course here we're talking about physical systems as well. So here we have our sensors, our machinery, and the like. So basically we want a verification and validation of complex systems, or systems of systems like you call them, develop metrics, security, privacy, safety, resilience, adaptability, and the like. So a whole heap of QoS comes here. Then we consider again the roles of humans to improve understanding of human knowledge and behavior. So basically humans become part of the solution of the problem, and they are services. And they are services which are active services, they're not passive services. In passive services, you have a problem, you ask for an answer, the answer comes back and it stops, whereas the human is in a position to change completely the computation and restart the computation, even maybe from scratch. And of course, at the end of the day, a lot of risk management and uncertainty. So what happens today is, if you look at several of these approaches which we have on big data, one of the pervasive issues here is that you have a lot of uncertainty. So we're talking about different types of analytics, for example, and uncertainty is an important element here. Now finally, we have development and deployment. So here we talk about effective and reliable system integration, interoperability mechanisms and the like, which is a heck of a problem, of course. Universal definitions for representing ultra-large heterogeneous systems. So our systems are becoming larger and larger, more complicated in essence. And of course, we want interoperable solutions to the extent that we can do that. Advanced abstraction mechanisms, programming languages and the like. We want new generation programming languages which are much more effective than the Javas and the JSONs of today. And of course, at the end of the day, we want to develop new methods, if you wish, software engineering methods for this emerging paradigm, possibly based on Agile, DevOps, and these sorts of, let's say, methodologies which are far more, if you wish, flexible than the ones that we had today. There's not a single sort of approach here, so you have different options and you have to pick and choose. So these are some of the challenges which I have in mind when I came here this morning to discuss with you. And what I'm going to do is I'm going to touch on several of those. I'm not going to give you answers because I don't have them, but I'll give you some examples at the end of the day. Now, let us start moving into, yes?
Do you have any idea, any clue about natural language processing?
Absolutely, it would fall here.
Okay.
Advanced abstraction mechanism. So here I'm talking very broadly.
Yeah.
So natural language could be very much part of that. And in fact, I have some examples in the end of my talk which touch on natural language. I mean, they're not real natural language processing, but they have elements of that.
Thank you.
So let us move to a slightly disconnected, I should say, field, which is smart connected factories. Let me explain to you what happens here, and then I will come back to the issues that I mentioned to you before. So this is what's happening today. So essentially we have smart factories, and these factories, they have, if you wish, they're based on some kind of a supply chain. And this is a smart supply chain which, of course, uses modern technologies like the cloud, for example. And you start by looking at the elements inside the smart factory. And as you're going to see here, the different elements which are very important or important factors. You have water reservoirs, you have energy, of course, energy supply. And then you have all sorts of inbound logistics, of course, of materials to create a particular product. You have a number of suppliers, and then you start processing the materials to create a final product that could be an electronics product, could be even a service or whatever. And at the end of the day, here in this supply chain, or this bus, if you wish, whichever way you want to call it, you connect your suppliers to the customer. So the customer becomes a driver of the entire process. So the idea is you don't stack up your products on the shelf in a warehouse, but you let the the customers drive the creation of new products and services. And this is happening real time. Now, at the end of the day here, you have a lot of data flow, of course, between these entities, but you also have material flow. So materials are being shaped and changed continuously. They start from raw materials, and at the end of the day, you produce the product, which could be, for example, a laptop, could be a smartphone, could be anything. And as you see, you have four interrelated elements. You have the product, you have the processes and the equipment, as you would expect here, and you have also the organization which tries to put all these things into motion. And you have, unfortunately, this is a slide which I borrowed myself, a human who is a little bit smaller. I don't agree with this picture. I think this human aspect should be a little bit bigger than that, but that's another take. And here, as you look at this slide, you have manufacturing, you have all sorts of other services like marketing, of course, You have services which are not the SOA services, but these are the services which are associated with the product. In other words, it's maintenance of the product, new releases, and improving the performance of a particular product. So this is the service in the jargon of course, the business people, and maybe under the Porter, if you wish, definition of value chains. And it's not a technical element. Now you have procurement, technology development, and the like. So there's a whole heap of ideas, and if you wish, techniques which come from divergent parts of computer science, and of course manufacturing and mechanical engineering, which come together here to offer a solution to these kinds of environments. I don't claim I have very, if you wish, sophisticated solutions, but we have done a bit of work probably in the last 10 years or so in that particular area. So I'm going to show you some examples. So let's move that a little bit further. Let's look how these factories work. So here is the slide about the smart connected factory in action. And as you see here, you have also elements which are important to this particular conference. This is your IoT stuff. So you have various sensors and machinery which is interacting. So the idea today is, if you look at these smart factories, you have machines talking to machines. And I'm going to give you a few examples. It may seem futuristic, but it isn't, because this is really happening today. If you look at factories like the large automotive factories, BMW, Fiat, and the like, they have a floor. The factory floor is full of machines, and these machines have intelligent, or if you wish, smart devices which talk to each other. They talk about production capabilities, they talk about the status of their processing, and they report on errors if the errors happen. So there's a lot of things happening in that particular area. And everything falls under the banner of real-time monitoring. So we monitor every inch and every corner of the plant. We need to know exactly what is happening in the plant, be it a machine is malfunctioning, or be it that we have a material which is of substandard quality, because this is going to affect our production. Now, we also have automated processes in motion. So these are end-to-end processes from the design of a particular product up to the production of the product. And these processes are very standardized. So basically, you know at each step of the way what is happening, what materials you have to use, what quantities, what characteristics the materials have, what weight, what temperature they need to have, and so on, to generate the final product. And you also monitor the environment, because we are increasingly talking about a green environment, and we need to reduce the emissions to the extent that this is possible. So if you try to put that into context, and if you try to see the technologies and the approaches that we have today, you're going to find out that they touch on a lot of elements which I introduced to you in the previous slide with these research problems, the open research problems. Now, what happens is, if we try to connect things in, let's say, in a smart factory, we're going to see that we start from the bottom. The bottom is the plant processes. These are the control systems, these are the robots, these are the sensors, these are the smart devices. Our equipment, if you wish, and the operations of these equipment. So we need to put them into motion, we need to make them understand each other, work together in synergy. Now, at the end of the day, at the bottom you have something which is completely different. You have the enterprise, you have the enterprise business systems, like your enterprise resource planning systems. You have PLM, which is product lifecycle management systems, which tell you how to produce a particular product, at least the information about that. You have supply chain and so on, and these are completely disconnected. Guess what? They don't communicate. So what happens here is automated to a large extent, again here, but these two worlds completely fall apart. So you need to have people, experts, who are sitting here to talk to experts down there. So the idea is you want to have a continuum. And if you want to introduce that, you have lots of problems. So basically, this is what you want, is you want to have manufacturing operations here, like the definition of what you need to produce, the resources, the schedules, for example, how you're going to dispatch the work and fragment it into smaller pieces that people can work together and machines can work together. You want to execute the work, you want to keep historical information about what's happened in another situation to compare it and to contrast it with the future situation and so on. So this is how you automate manufacturing, and these are the events and operations which need to bridge the world of the enterprise with the plant, with the shop floor. And this is a lot of work which is happening today here. But there are a lot of challenges. This connection between this guy and that guy down there. Of course, this connection between especially product lifecycle management system and robots and sensors which are down there. This is a big problem because here you have a lot of information about how you design a particular product, and this is the, if you wish, the end product of your design. And you may have let's say cooperative design between several design teams who design a new product. You have all the information about the product and it stops here. It doesn't percolate down there. And of course you want to connect that. And you have limited point-to-point connections, lack of visibility, and you're not able to identify how work progresses from this point here when I have a large order from a supplier down to all the way that my product or the products which I have in mind are, let's say, produced in collaboration probably with other enterprises and other factories. So there's a lot of open problems which are very, very interesting in this field, which can come, of course, into this conference. Now, let us move to another field here, which is equally important, is big data and analytics in smart connected factories. And you're going to see there's a lot of open problems here again. Moving a little bit fast. So we have a lot of information about suppliers, partners, machines, components, materials, devices, humans, you name it. A heap of things which are quite disconnected. We need to understand how they need to work together, how they need to operate, how they need to be more productive. We have production processes and all sorts of data, production, distribution, marketing, sales, you name it, data. So whole heaps of data. Now, if you want me to impress you, this is the only slide I have today to impress you. This is the one which, not this one, the one which is coming here. And you probably haven't realized how much data a factory produces. So I'm going to give you some statistics. This is a typical factory. It's a factory which reflects data which is generated in one of many production lines inside the factory where they produce a particular product, a single product only. So we're talking about 150,000 samples of data per second. It goes to 9 million when you estimate it in a minute. In an hour, 445 million samples of data, 4 billion per shift, human shift, which would be roughly 6 hours or so. Then it goes to 13 billion samples per day. And if you look at it per yearly basis, you have 4 trillion samples of data. Massive amounts of data. And unfortunately, a lot of this data is very fragmented, so you don't have a holistic view. You store information about your products here, for example, information about how you design a product, about the performance of, let's say, the manufacturing systems. You store information about how your robots behave and all that, which is perfectly fine. So this is where the masses of data come from, but they're not connected, so you don't have visibility, or you have many partial visibility here. So you want to have a more complete picture. So sources can be external sources here, users, social media groups, focus groups, what have you, who comment on the product that you produced and how it behaves in the marketplace, for example. You have internal sources, like the ones I mentioned to you. These are your sensors, the ERP systems, the processes themselves, the robots and so on. Well, actually, sorry, they're not the robots, they're coming down here, M2M interaction, so sensors and robots come here, apologies. But these are other systems beyond, if you wish, the machines and robots themselves. So, and finally, you have the interaction of machines with machines, smart sensors, robots, all sorts of equipment, and so on, which try to work together in order to solve a particular problem and generate a new product or customize a product. So as you see, there's a lot of data which is floating around, which is nevertheless is captured, but is not used effectively. So what we want to do is we want to use this data more effectively to improve the decision-making processes and our analytics, of course. So here we exceedingly talk about predictive and prescriptive analytics. So we're moving to the new generation of analytics, which involve all sorts of new technologies, including, of course, machine learning.
Mike, can I?
Yes, absolutely.
Yeah, the figure is nice, but it's a bit exaggerating, because here you assume probably it's not you. I know
it's not me. It's actually GE. All the fault comes from GE.
But my point is that you assume here that the data are not overlapping. Honestly.
Oh, it is overlapping.
But it is overlapping.
Absolutely,
and
yes.
The measures here do not consider the overlaps. That's why.
Yeah, that's true. So they consider each, yeah, you're absolutely right. They consider each source in isolation. So if there's overlap, which there is a lot of overlap between these sources, this is ignored. So they talk about masses of data from the marketing, masses of data which come from the production, masses of data which come from the factory floor, monitoring, pressure, I don't know, let's say historical data about products and so on. But they looked at it completely in isolation. They didn't say 20% or 20% overlaps. Let's exclude that from the picture. No, they don't do that. But this is where the interesting part comes in, because the intersection of these sources is the elements that you have in mind. This is the common part, and this is what we have to look at to find the synergies. Absolutely correct. Okay, so if we want to move to smarter analytics, we want to be able to answer a few questions, important questions, if you have especially a human in the middle. First of all, we need to understand the performance of our assets, and then the integration of these elements. So how can we optimize the plans that we have? How do we do in-depth failure root analysis, for example? How we detect warranty issues if something goes wrong much faster? What is the life expectancy of a particular machine? What happens if a machine is misbehaving? I had this problem this morning. I brought my computer, it refused to work, it doesn't work. So we have the plan B and plan C hopefully in place. And luckily I was able to get a copy of my slides. Otherwise I would be looking at you now and trying to think what I'll say. Anyways, so basically, how do we create the highest and cheapest quality products? So this is where the equation comes, not to spend too much, to overspend, and generate products of the right type of quality. And of course, how we try to reduce the variability of the products and keep them under control, so we have products which are really targeting a specific customer section. So these are the questions, or if you wish, the drivers of the improved resource and process performance, which require better, smarter analytics. And there's a whole heap of research happening in this area. I can give you a lot of references in case you're interested. Now, this is where smarter analytics lead to something which I call systems of insight. So recently we came up with the concept of systems of deep insight. So these are the systems which give you a lot of information by unearthing all these gems that Roger was referring to, the overlaps between the data. So hey, look, you have a marketing strategy, but if you go that way, this is going to impact the performance of the product because you're not going to be able to build it. So you're marketing something completely wrong, or you're misinforming your customers, things like that. And this is really important here. So you have, so Richard was completely correct here, because we have different pieces of data and a lot of overlaps here. So we need to understand this data and inform, let's say, the systems and the people about possible actions. And we improve our processes. So this is a virtual, if you wish, virtuous circle here, because this is a continuous circle of improvements. It's a closed loop. So you try to improve by understanding the context, by understanding what is happening, and by improving your processes step by step. So there's no big bang approach. If you think that we can take our processes and we can improve them immediately, that's not going to happen. We do it stepwise. And as you see here, you come with smarter products themselves, and you have product insights. You have insights about your customers, about your risks, about your sales, about your marketing, and you connect all those. So basically all this is the information that Richard alluded to, but here what happens is it starts becoming connected, and we try to identify, of course, and the overlaps. If we look at the key elements of the industrial Internet of Everything, to come back to the picture I gave you at the beginning, we look at three aspects, if you wish. There might be more. This is again a slide which comes not from me, comes from General Electric, but I think it's an interesting slide. It tells us that we have intelligent machines. We can connect machines and facilities with advanced sensors, smart devices, controls, and software applications so they can start talking to each other. Then we have advanced analytics, and then here we have people at work, and this is roughly what I mentioned to you before, so let me skip this slide because I don't want to waste a lot of your time. Let me move to a field which is very interesting, and this is the culmination of all these activities, and this is called Industry 4.0 or Industrie 4.0. He probably doesn't like it. Too complicated.
Police the fonts.
Okay.
Where we were. Oops.
Yeah, this one. Okay. So basically, what I mentioned to you about the smart factories or the factories of the future, which is again a big, if you wish, element of research in the H2020 program. This is Factories of the Future. It's called it slightly differently in other European countries, and especially in Germany, where it comes from, because it originated from the big industry players in Germany, like the automotive industries, the pharmaceutical industries, and of course the large, let's say, industries which create advanced machinery and the like Siemens and so on. And of course medical systems as well. So what happens here is this is the fourth industrial revolution, and this is the big picture. So basically we want systems which have four characteristics. This is again not my slide. I borrowed a lot of slides from different let's say people and different companies. This is a very interesting white paper. In case that you're interested in that field, this is a must-read paper. It comes from Capgemini and it sets up the scene. And it says that in this particular field we want to have systems which have four characteristics. They are first of all connected, which is obvious, of course. So we have the internet, we have mobile systems and the like, inside our physical systems, our sensors talk to each other, fine. Our systems have to be aware, they need to be context aware, they need to understand the context under which they operate. And of course, if we talk about smart products, they're equipped with all types of sensor technology, so they inform the surrounding environment about things regarding their production status. How far they are in the production, if the production is in time, if the characteristics of the environment are correct. In other words, if you have the right pressure, if you have the right temperature, if you have the right humidity, and so on and so on. The systems have to be intelligent, so the products become more intelligent, and somehow they're part of the computation themselves. So you see, this is a picture which has futuristic elements. And of course, at the end of the day, our systems and the products are responsive. In other words, they answer to questions somehow. Maybe in a limited fashion, but they do. Now, if I want to put things into perspective, the next slide tells you a little bit about that. It's a very silly example, but it gives you an indication of what's going on. So here you have a customer order. So this is an order that I was talking to you about. So you don't have a product in stock. You don't have a product in warehouse. You need to create the product real time. You need to service this customer, because this is the way that factories operate today. If you think that they produce hundreds of thousands of cars and they stock them on the warehouse, they don't do that. It costs them a lot of money, unfortunately. Now, so here we have our cyber physical components which are carrying the processing here. And the first thing that you ask, what is your price for this operation, right? So you want to create a product, the first thing you think is about the economics, how much this is going to cost. And then you have cutting sections, or stations rather, which cut pieces of metal in order to produce, let's say, an equipment or part of a car, a door, or whatever. And they say the prices. I can give you 150, but I have no capacity. I'm fully booked until, let's say, the end of the month. So if you want to wait, fine. If you don't want to wait, find someone else. So number 2 says 30. I'm set up for this material class, so this is more promising. And 2 says 50. So at the end of the day, of course, you try to choose one of these 3 stations, and you operate in this fashion. So basically, each step of the way, the cutting station reports to you about what it's doing, how far they are in the process, what problems they have at the moment, or problems they may emerge in the future. So this is how our machines and how our factories are operating today. And as you see, there's a lot of communication on machine-to-machine level, and also material flows and data flows in this picture, which are not shown. So there's a lot of interesting elements that we have, and a lot of interesting problems that we could solve using these types of approaches. Now, if you want to control things, here we put things into perspective. It's a similar picture to the previous one, and here there's something which we call a control tower. So all the information is propagated to, if you wish, the brain of the operation, which is the control tower, which tries to control all the different types of activities inside the factory floor. And to put things into a better perspective, this is applied on a context which is very much standardized. So for those of you who understand manufacturing supply chains, this is the SCORE model. SCORE is supply chain operations resource model. And basically it deals with 4 or 5 actually processes. You plan the product, you source the materials for the product, you make the product, you deliver it, and maybe there is a return. So these processes are all standardized, and they are being defined to a lot of detail. You have information about the vocabularies of all these processes. In other words, you don't have any semantic problems. You have complete definitions of all the processes on those levels. And if you look at the SCORE, if you wish, the R was reference. I was looking for the words, was not resources, reference. So it's a supply chain operations reference model. And if you look at the definitions of SCORE, you're going to find that they're about 1,500 pages long, with all these details and all these characteristics in place. So this means that you have standards which are driving your processes and driving the production. If you don't have standards, of course, everything fails. Now, what I try to do very quickly, and I think I'm doing reasonably well with regards to time, I try to give you elements of the big picture, a few things about research problems, open problems, and the like, and then I try to put that a little bit into context by giving you examples from Industry 4.0 and explaining to you how the future technologies are moving and evolving. Now, if we want to address some of these research challenges, I have a few examples from our own experiences, especially in the context of very large projects which involve a large number of partners. And one of these projects, I'm very happy to mention that Ernesto was part of it. This is from his previous life before coming to this nice part of the world. And I do have some ideas and some thoughts that I would like to share with you. So let us look at the next slide. This is, I have to warn you, it's a complicated slide, but I'll try to explain that to you. So basically, we look at the first challenge, and the first challenge was about systems engineering and architectures in general. And what we did is we tried to come up with an architecture for the context of Industry 4.0. And in particular, what we did here is we have, if you wish, separated our systems into 3 layers. The first thing is how we define and configure our products, is the product configurator. Then you have a language which you use to define your products and configure your products, which has natural language elements, and this is where natural language comes into play, and I will give you a short example. And then you have specific knowledge structures. So these are the structures about how the products are defined. So you have complete information about a particular product. Let's talk about a computer or whatever. So here you have a complete definition about all the modules which come into the computer, which are the modules, how they are related, and you separate them into something which are called product families. So a computer has 2 or 3 product families inside it, and you separate all these product-related material into taxonomies. And here you have information about the product itself, but you don't have information about the processes which generate the product. So essentially what you need to do is you need to understand how the individual components are related to each other so that you put those things into motion. And this is something which is happening here. It's called the production plan. We try to put things into motion. But let me go through that particular slide. The other thing that you have is you have a product library where you have information about how you created a product in the past. So if you want to create a product which is slightly similar to what you have in your product library, you try to compare and contrast to find out what are the similarities and so on. And you have a repository about suppliers, products, services, production plans, and quality assurance. So all these elements we call collectively blueprints. So these blueprints are manufacturing blueprints which create a complete definition and production plan about the product semi-automatically by involving users. So the idea is you have a user who comes here, a customer, orders a product and defines the characteristics of this product by using a product-oriented configuration language, POCL we call it. It has a specific syntax, it has a specific grammar. I'll show you some examples, and it's platform independent. So we're using an approach, of course, an MDA approach. This approach is completely independent of a particular, if you wish, a structure. And here what we have is we have product-specific knowledge. So this becomes a little bit more, if you wish, platform-specific. So this is the platform-specific model. This is the platform-independent model. So here you describe products in general, and here what happens is these products, the description from the user or the experts, become more concrete because they lean on definitions of specific product taxonomies. So this is your product-independent module, and this is your, platform-independent, and this is your platform-specific. Now, the other thing is, once you have that here, you transform the information that you get from these products and from these definitions that the user gave into a series of, if you wish, metadata. These metadata regard suppliers, products, services, production plans, and quality assurance, and it becomes a series of, if you wish, blueprints. And I'm going to show you an example. So this is a little bit abstract, but I'm going to give you an example. And out of these blueprints, you create, let's say, if you wish, customized products. And at the end of the day, you have standard products specifications which exit to a complete plan. So at the end of the day, what you want is you want to have a complete plan, how you're going to produce a specific product. And you get input about all this type of information from different types of users, from designers, from architects and engineers, who are, of course, the informed people, or from customers who are lay customers, but they all collaborate to generate a single product that, at the end of the day, satisfies the customer needs. This is a rather conceptual architecture. Of course, we have implemented several parts, and I will show you the implementation, how it looks like to put things into a little bit of a perspective. So in the next slide, what I'm going to do is I'm going to concentrate on that example here, and on this here, the product library and the blueprints, and then I have a few ideas which I want to share with you about this particular language here to show you how it works. And this is where I stop. So the next slide is, again, it goes into R&D challenge number 3, knowledge structures and processing. So we use an advanced metadata, if you wish, environment and knowledge-based environment. And we describe 5 kinds of things here. We describe the supplier blueprint. So this is the supplier who supplies, if you wish, materials or maybe parts of a product. We have the background of the company, the products, the services, the skills of the people, the key processes, and capability and capacity in case that we want to use this type of organization in our production. This is connected to something which is called the product blueprint. And connected in both ways. The product blueprint tells you about the product family, in other words, computers, specific computers or whatever, the materials that we use, the product definition, the production capability information, the sensors that we use, the environmental information and the like. So all this information is being stored into a structure which is called product blueprint, which we can manipulate, we can process that structure. This structure is connected to supplier structure and connected to a service structure. So this tells us about the service types. And the service types here are things like maintenance, new releases of the product, and improving certain parts of the product. So it's not the service in the service-oriented architecture. So it's more of a general service which goes together with products. The production plan, so here you have information about the workflows. You have the events and data collection elements, resources, devices and equipment which is used, including the IoT. And here you have the quality characteristics, production performance KPIs, monitoring of product sensor data, production KPIs, rate of production, capacity, working progress, and all these which is an extension of Light Owl, and they are interconnected. And so you can find about the product, who is the supplier of parts of the product, when it was generated, under which conditions, store these things. You can define them, of course, in a concrete fashion. You can store them, you can manipulate them, you can compare them, contrast them, extract information, delete information, improve information. You can query them because you store them in a repository. And of course, at the end of the day, what you can do, which is more interesting, is not only that you publish them, but you aggregate them. So you take a structure like this, which represents part of a product, and you connect it to another part of the product. And your processes become slowly end-to-end processes. So you build your system in a discrete way. And this is something that we have in mind. We are working together with a laser production company, a huge one, a European one, of course. And we want to generate laser machines, which cutting machines, drilling machines of the future. And what we have here is we have all sorts of product description requirements, product composition on demand based on family trees, quality criteria, constraints, performance, parameterization, and consistency checking in terms of a language that we have produced ourselves. And this is a very lightweight language. It's a domain-specific language, so it's specific to manufacturing, but elements of that language we can use in other, of course, sectors, if you wish. And if we specify the characteristics of the product here by using this language, we transform it into these, if you wish, structures, and which we can reuse and configure. So in the next slide, I'm going to give you an example of this language, and I think this is more or less where I'm going to stop. So this is a declarative language. It's geared to what product design and customization. So the idea is if we use this language, we can collaborate. We can be customers who have very little knowledge about the technical characteristics of our product, but we know what products we want, and we can work together with, for example, production engineers or analysts in order to create the product interactively. And we also use CAD and CAM tools, so we can have blueprints, real blueprints of the products. We can see this product, we can visualize it, and we can start specifying what changes we want and what elements we want to keep and what elements we want to improve, things like that. So we have user goals and these or sub goals. These could be soft or hard. So we specify what we want to happen and what we would like to happen. And we give options to the system to come back to us with, let's say, different, if you wish, possibilities for constructing a particular product. We have also, we specify policies, and we specify user preferences. And we have all sorts of operators, temporal operators, logical operators, constraints, and constraints on the resources that we're using, which we can't specify. Now, this is an example of a textual use, so this comes closer to the gentleman that asked about natural language. And it says produce two completely independent precision 5 to 7 axis laser cutting machines, welding, and drilling machine with a single utilized structure. So this jargon, this language is very concrete because it tells you about a specific product. So we don't allow, of course, unlimited natural language, but the language is very, very specific and is very attuned to the product that we have in mind. So we explain what the product does. Will be used for cutting, welding, and drilling. Medium-sized 3D parts. So this gives you more information about the product that the customer wants, with a unique moving beam and system. So this is again very standardized information that you, of course, provide as a user. And speed, weight, things like that. And basically, this is the information that you put, if you wish, into, oops, sorry, wrong direction, into these blueprints. So all this information starts being input into these blueprints, and we have here the suppliers of parts of this product. The welding part, for example, comes from a supplier in Spain or in France or wherever. The production, let's say, workflow. So this is how we produce this sub-part of the product, and we put it together with another product, a sub-product, and we connect the processes to create the whole product. So you have different workflows on different levels. They're not on the same level. There's a meta-level workflow which puts individual workflows, how you create individual components together to create the whole product. This is the abridged syntax of the product-oriented language. It's very, very brief, of course. Here is an abridged version. So you have things like the product parts, the parts that you produce in-house, the suppliers, the outsourced suppliers, the in-source, the product, the configured products, products which cannot be configured, so parts that cannot be configured, services, quality of products, compliance, KPIs, different types of KPIs, all sorts of products which cannot be configured, so parts classes which fit into the product. So you have a complete description of your product and production environment by means of this language. And at the end of the day, you can use it in a very simplified form because you don't see that part. This is the part which is very much dependent on the characteristics of the platform that you have in mind. So this is the platform-dependent model, whereas you use as a user a platform-independent model, which is much closer to your needs. So this is what's happening here. This is the visual form. So you have here these parts of the laser machine that I was talking to you about, which you can see on a CAD diagram, and you start connecting one to the other. I don't have a video here, but basically imagine that I produce these parts by putting these components together and explaining the components that I want to connect to each other. And I also place some characteristics here. So this is the 3D visualization. I can also put parameters, and I can put these types of parameters in conjunction with that. So I can have a visual diagram together with a textual diagram which specifies my needs and so on. And I can also put my constraints, what I want to have as a mandatory part, and what I have as optional parts, if there are optional parts here, for example, just to give you a glimpse of what's going on. So this is this type of language that I mentioned to you, which we have already developed to a certain extent, and we have here some of the, if you wish, user interface parts where you can customize the product. This is your library. These are the diagrams from your library. You pull them up and you can manipulate them on the fly, and you can pick and choose and change the elements that you want. Here you specify your constraints, the product characteristics, and everything at the end of the day is being, if you wish, verified that you don't put things which do not belong together, hazardous elements, for example, or elements which are going to increase the value of the product, or elements which are inferior to the product that you want to create. So there's a lot of constraints and a lot of, if you wish, verification which happens under the scenes. And this is roughly what is happening. So if we want to put things into motion, this is the last slide for today. So basically what you do here, you have the individual components that you're going to put together. You have different valves, for example, torches, cutters, optical focus controls, which are the materials that you want to put together. Each of them you describe by means of these 5 blueprints. These are the individual blueprints which we had before. And then what you do is you compose these blueprints and you generate a single blueprint which represents the entire machine. And here you also have the information about the entire machine, but you also have the information of how you construct it. In other words, the workflow. So this is generated by means of these blueprints that we connect together. And this is a schedule about how we produce a cutting and welding laser production plan. This is in very, of course, very sort of, if you wish, simplified form. And this is information which you input in these blueprints in order to be able to produce the final product. So this is something that we've been working on for the past almost 5 or 6 years, and we have little elements of that which we can demonstrate, but there's a long way to go. So I'm going to close the description of these types of environments and these types of ideas of the Internet of Everything by a slide, which is a concluding slide, and maybe we can have a few questions. I think I'm doing reasonably okay with time. So basically, we want our products to be optimized, customized very quickly, driven on demand. We have collaboration, which could be spontaneous, and of course, our products need to be sustainable. In other words, we have compliance, which is leading our products of the future, and these can be involving different types of, if you wish, stakeholders, like of course the mining and the farming, if you wish, communities, the supply chains, the manufacturing plants, the distribution, and finally the customer, who is responsible for driving the entire chain here. And we're talking about exceedingly, if you wish, complicated and expensive products here in many cases. So we translate from owning and operating dedicated assets, including people, expertise, and equipment, to sourcing and orchestrating on the fly our products and our services. And this happens on a global scale. So it's a completely new paradigm, if you wish, an emerging paradigm for that particular field. Now, the customer is pushing demands, not the companies, and the customer is the owner of the entire production, if you wish. So we have a flexible production of smaller customized production volumes, not masses of products, but products on a smaller scale, much more customized, much more flexible, much more adept. And we have modern knowledge and information which is driven, optimized and automated and stored and reused continuously to improve the production processes. So I guess this is the last slide for today. Thank you for bearing with me so early in the morning, and let's hope I didn't manage to confuse you by sort of let's say explaining to you all these sort of futuristic scenarios and ideas, but let's hope that this is an interesting field for you and this may lead to some future collaborations. Thank you very much.
Thank you very much, Mike, for this very interesting keynote. We have a lot of ideas, and I hope a few questions after this interesting presentation. Want to start? I'm going to start. I'm sorry.
If we need to start, I can start.
He's going to ask the difficult
yes,
questions.
exactly.
Otherwise he was hesitating.
No. I just want to understand. You were talking about production blueprint. It's a very nice concept that I saw this morning. Really nice. And I was wondering, what we are putting inside. We are putting just the metadata of items, entities.
True. Yes. So basically, what you do is you don't process on the basic level. So you lift everything up on a higher level. So it's metadata, whatever you want to call it, semantics, whatever, any word that you want to pollute, you throw there. But essentially, what you try to do is you try to abstract from the characteristics of the product or the process that you have in mind. So it could be also a medical product. It's not necessarily a physical product, right? So it could be the patient. So you want to restore a patient to the peak condition, right? Whatever. Looking at profiles, disease history, diet information, whatever. This information is very widely stored in different sources. So what you want to do is you want to compartmentalize it, make it more concrete, and then what you want to do is these individual pieces, you want to connect them together. So you want to have a complete picture. And once you have that, you store this information, and you retrieve it, and maybe you connect it to other information about the same patient. So you can compose it on the fly, you can query it, you can compare it, and you can take statistics. So you can take, for example, patients or products depending on, let's say, age, depending on ethnicity, depending all sorts of characteristics, dietary characteristics, what have you, obesity, all types of characteristics, and you can bring the samples, and you start comparing and contrasting to try to educate yourself and find solutions on the spot. I'm sort of moving to slightly different domain just to give you a broader example.
But my point was, where I didn't understand is related to this blueprint. It's something that you consider as static?
No. It's dynamic, it's continuously evolvable. So the information is getting stored, and what I want to do in the future is I want to optimize them. So basically the information which is stored there, which is specific to the product I want to create, is getting optimized. I do have concrete parts which are about the product family. So this is cast in stone. So I know that, the internal elements of a computer are these boards, the display board and the sound board and this and that and so on, and what are the characteristics of the, let's say, the screen or what have you, or the power or whatever, the screen, which doesn't work in my case, right? And you have a complete description of that. This is static, it doesn't change. But what changes is things like performance, like price, like the extras that you want to put on the computer to get a much better, a much faster, let's say if you want, module.
Yeah, and this is my point.
Yeah.
So why there is no separation between static information and dynamic ones in your presentation?
Well,
because if you want to optimize their storage somehow, you are duplicating some information.
No, you don't duplicate. You don't duplicate it. It's stored in one piece, in one location. This is standardized. It's stored there. But what you want to do is you want to connect the dynamic characteristics with the static. You want to associate them. You want to say this is a product which comes from a particular product line, from a particular product family. These are the general characteristics, but these are the specific characteristics I want to customize. In the general characteristics, you don't have information about, let's say, concrete things which you want to customize. So this becomes part of the dynamic. So there's a standard, if you wish, configuration, which is very standard. It works well, you know how it works, and then you say, well, let me tweak some of the parameters. What happens, for example, you can have what-if scenarios. What happens if I put a lighter, let's say, power module or whatever, or a faster processor? How would that behave? How much this is going to cost at the end of the day? So these are the things that you want to change, and you want to get to associate them with concrete parameters. So you make the you don't duplicate, you just make the link. So these are pointers in C++ or whatever.
Thanks, Mike.
Questions? Yes.
Well, regarding people, I think it makes sense to consider those new approaches that are user requirement driven. And there are new approaches also taking care about the new user interfaces.
Absolutely, yes.
I don't remember how is the context is something like push or
Yeah, that's right.
user interfaces or something
True,
like
true,
that,
true.
more related to people in this case.
Absolutely. I must admit that I didn't look at the user interfaces per se because I was interested to explain to you a little bit more about the language. But the idea is you look at visualization techniques and all these types of techniques that you mentioned, which can come on top to make things much more easier for the user to understand. So that's true. But this is something which I didn't discuss too much here. But this is a useful piece of information, useful ideas of how you can, of course, improve the situation that I mentioned.
What about the current state of the industry 4.0 in Europe, United States? How do you see things now and coming next year?
There's a lot of research which is very much, I would say, driven by industry. So, of course, there are a lot of research which is happening from universities, but if you look at the context of Industry 4.0, or the equivalent in America, which is called SMLC, Smart Manufacturing Life Cycle Consortium. So these guys are driven by large industry representatives. So the research that universities are doing is very much down to earth and very much, if you wish, applied. In a sense, of course, you look at new research areas like, I don't know, machine learning, for example, data mining, I don't know, prescriptive analytics, descriptive analytics, what have you, but you try to apply those into context. Now, if I'm going to say to you that there are solutions, the answer is no, they're not solutions yet, but there's a lot of activities which are happening at the same time, and in many cases, a lot of that stuff is confidential, so it doesn't come up to the public before they produce, let's say, a concrete product. And there's a lot of companies here, so it's not only manufacturing companies. I mean, you have BASF, you have Siemens, you have the automotive industry, you have pharmaceutical companies and so on, but you also have a lot of large companies, computer vendors. I mean, and also you have companies who are, I guess, providing you with services. You have companies like Deloitte, PwC, Capgemini, and so on, who are giving you, I guess, all these types of consultancies, right? And this is where they make the money from. So all these people are collaborating with each other. So it's a huge initiative. And it's not driven by only technical, the technical world, but it's also driven by economics and by business. So, and of course, manufacturing and mechanical engineering as well, because this is very much part of it. And of course, what is important is that you have also the robotics people. So these people are very much involved into these types of, if you wish, environments.
And about Internet of Everything, then not related to the question about people and social networks and sentiment analytics. How people are really using that industry?
No, not yet. No. I'm basically the idea. What you want to do is you want to expand that into the social media. So in a sense, you have your it's a how can I put it? Something which may happen in the future. It's like a wish list. So it's wishful thinking in many cases, that you would have your customers coming back and reporting on their experiences, and this is broadcasted on the social media, and you create a lot of such information which is publicly available, so that if I am a new customer, to see what happens and try to extrapolate and understand, you know, what's going on and how good or how bad you are. And this is information which is also useful because it improves the performance of the products. And of course the characteristics of the products, and maybe at the end of the day makes the products cheaper or what have you. Excuse me.
Okay, I don't know if we another question. And we are going to thank you again.
Okay. Well, thank you very much. Thank you. Thanks, Richard.
So let us have a break and have a nice coffee.
Yeah, sure.
Yes.
Nothing against it.